So let's now move on to the dual simplex algorithm and the setup for that. And as I said, a few more slides here, we'll take a break. Not a half an hour. Okay. Simplex algorithms apply to problems with constraints in equality form. So if we want to solve the dual, the very first thing we have to do is convert what were a bunch of inequalities into equalities by adding the so-called dual slabs. I'm labeling those as D here. That's supposed to be suggestive notation because they do in fact correspond to these reduced costs in the primal way of thinking of the model. I mean, these things are full of notation that come out of thinking about both versions of this thing, which is useful on the one hand, can be confusing on the other hand. So there's my problem. It's not in standard form anymore, but it does have equality constraints, and it does have some free variables. We can apply the simplex algorithm or a version of it to that problem. Okay, so dual simplex algorithm, the setup. It is useful to think, at least I find it useful to think of the constraint matrix in the dual as partitioned as described here. All right, so imagine you have a basis from the primal. So this describes a submatrix of the matrix A. The matrix A I can think of as making up the columns at the left of my constraint matrix in the dual problem. Given this B, I can imagine sorting the rows so that the B part occurs at the top. And then I can take the identity matrix that corresponds to this D matrix and sort the columns so that the B part looks like this and the N part looks like that, and things line up. All right? The point is, I've got a basis out of the primal, and that's going to play a key role here. You will see it in a moment. And to think about that and how we do our computations, I want to permute the matrix around so it has this form. Okay? It's actually pretty important. Is anybody not clear what we just did here? There'll be plenty of stuff where you aren't clear, and I won't ask you if it's not clear, because I won't know a short way to clarify. But this is important. Okay? So, given a basis B, the corresponding dual basic variables are pi and dn. That's definition, if you like. dn are the non-basic variables. The corresponding dual basic solution is computed here. I'll come back to that in a second. B is dual feasible if a certain condition holds. So, let's at least convince ourselves that this choice of, by taking pi and dn, actually is a legal basis. And for that to be true, the corresponding submatrix has to be non-singular. But that submatrix is made up of the A part and the IN part. The part in the middle is gone. All right? And it's easy to see that that matrix is non-singular. The IN part certainly is non-singular. It's an identity. All right? It's going to be non-singular if and only if AB is non-singular, which it is. So this definition always gives you a subset of columns that determine a non-singular matrix in the dual. Right? And the remaining, well, that's the basis matrix. If that's the basis matrix, this IB part has got to be the non-basic part. And our rules for basic solutions are we set the non-basic variables to their bounds. So you set dB equal to 0. If you set dB equal to 0, capital D because those are values associated with the D vector, right? Then you can see here by substituting 0 for that thing in here, you can solve AB transpose pi equals CB, which gives you this formula for the values of the pi variables. And then by substituting in those pi, multiplying by AN, subtracting from the right-hand side, you get the DN variables. Right? And that this is the definition of dual feasibility in that case is pretty clear, right? The variables are supposed to be non-negative. If, after this computation, they turn out to be non-negative, you have a dual feasible solution. So now comes an important observation for which I really can't give you a detailed proof, but I can certainly give you the idea. And that observation is this: we may assume that every dual basis has the form that I just described. That is to say, we start with a basis in the primal. That defines for us a basis in the dual as given on the previous slide. And I don't claim that every basis of the dual looks like that. What I claim is those are the only ones I need to look at. Right? I don't need to look at any other bases of the dual. And to give you a rigorous proof of that would take us, at this point, too far afield. It's not that it's so complicated, but it would take us too far afield to fit in today's presentation. Nevertheless, I give you the idea. All right? Suppose you take just a basis for the dual. So now this is just a submatrix that's non-singular. That's really all a basis is, submatrix that's non-singular. And we take the non-basic variables and set them to bounds or whatever and solve for things. Well, suppose you had a basis in the dual in which a free variable, one of these pi variables, was not in the basis. Now, pi variables, they're free, they don't have any bounds. And I said non-basic variables are supposed to be set to their bounds. So we have to decide what to do with them. What most people do is set non-basic free variables to 0. It does happen, just set them to 0. You could pick another value. 0 seems to be easy to work with. That's the choice typically that's made. Suppose you got a non-basic pi variable. It's at 0 in some basis. Just consider doing an iteration of the simplex algorithm in which that pi variable is the entering variable. Forget about whether it's got a good reduced cost or not. Forget about that. Just suppose you consider it as the entering variable. Well, if the entering variable is a non-negative variable, it starts at 0, it has to increase. But if it's a free variable, it could increase or it could go down in either direction, right? As far as the linear algebra is concerned. Now, in determining how far you can go or what are you going to do, what you do is you compute a representation for that variable in terms of the basic columns. All right? That's what this F-trans step is all about that we saw before. Representing a non-basic variable in terms of the basic column. Suppose you take this free variable that's outside the basis, you represent it as a linear combination of basic variables. They can't all be free variables. If they were all free variables, the columns in A would be linearly dependent. And they're not, because we have a basis in the primal. So there must be some slack that's in that representation. Well, by then taking this non-basic variable and moving it in one of the two directions, that slack is going to go toward its bound and is then a legitimate leaving variable. So then the pi comes in and the slack goes out. Do that for every pi variable that's not in the basis. In the end, you will get a basis that includes just the pi variable, all the pi variables, and other stuff. Now, if you apply the simplex algorithm to that, the pi variables are never going to leave the basis. Because the only way a variable can leave the basis is if it hits a bound. They don't have any bounds. So that, if you will, is the essence of a not so difficult proof, if you wrote the details, that you can assume all the pi variables are in any basis that you actually need to look at, even though there might be other bases. And this is the foundation of the dual simplex algorithm. Namely, we can assume there's a one-to-one correspondence between primal bases and dual bases. So we define what a primal basis is. For each such primal basis, we can write down a corresponding dual basis. We did it. Those are the only bases we need to look at. And this, then, I'm repeating myself, is the foundation for the dual simplex algorithm. Because what does the dual simplex algorithm do fundamentally? It solves the dual problem while you're staring at the primal. And in fact, what we will do is we will take a primal basis, but we will think of it as a dual basis and work out the steps in the algorithm. So that's how, at least I think you should think about the dual simplex algorithm. Okay, an important fact, we're getting close to the pause time here. So let's let x and pi and d are corresponding primal and dual basic solutions determined by a basis b. Now, right, determine one basis B for the primal, that defines a basis for both the primal and the dual. So I just speak about one, but there are two bases here. Right? And corresponding to those two bases, I get primal and a dual solutions, which may or may not be feasible. So what I claim is whether or not they're feasible, this equality holds. Always. Whether they're feasible or not. Well, by the weak duality theorem, if that equality always holds, right, as soon as we produce feasibility, we've produced optimality. And in fact, that's what the algorithms do. I'm sure you've heard this before. The primal algorithm has a primal feasible solution. It tries to make it dual feasible. The dual algorithm has a dual feasible solution. It tries to make it primal feasible. By this fact, which we will go through the proof of in a second, as soon as you achieve feasibility for the second thing, you have optimality in both problems. Right? And by the way, of course, a proof of the strong duality theorem at that point, if you believe the algorithm can be proved to converge. So let's go to the proof. Here's C transpose X, that's the thing on the right-hand side. Okay? So I've got a basic solution here. It's got the non-basic part and the basic variables. The non-basic variables are equal to 0. So if I want to compute the objective, I just have to look at the basic variables. That's this part. So C transpose X is just equal to the basic part. Right? CB transpose times XB. Good enough. Now, since pi is the solution of this system in the dual, which comes from a previous slide, I can substitute pi transpose AB for CB transpose. I've done that in the second equation. And now I have AB XB, but that's just the primal constraints. The non-basic part is 0, it's gone. That's equal to B, which gives me pi transpose B. And that's the desired equality. So that's really easy to prove. Right? So again, this is at the foundation of why we can do something called the dual simplex algorithm. So here then is a statement of the dual simplex algorithm. I thought I was going to put something else. Yeah. So again, we have some input conditions. We have a pricing step. We have two linear systems, step 2 and step 4 that we solve. And we have a ratio test. And we have an update where we change the basis and we update the inputs up here. I'm not going to go through a bunch of justification for why this is the right statement. But I do want to, well, I should say that, let's just say this one part here, which is that I'm determining in my pricing step an index I, indexed over the bk for k in 1 through m. Okay, so what this really says is that dbi for this selected I, remember the db variables are the non-basic variables in the dual. All right, that's the entering variable. So now that dbi we're going to allow to be positive. That's what that means. And then we pick an index j, which is taken from what in the primal are the non-basic variables, and that's the leaving variable. So in effect, viewed in the primal, you actually are picking the variable that leaves the basis B first, and the variable that enters it second, which is just the reverse. All right? So if you weren't confused before, sure as shooting you're confused now. Okay, so here are the two algorithms next to each other, and part of the point of doing this is to show you that they're really incredibly similar algorithms. All right? They both have exactly the same input, except feasibility is different. In the primal, feasibility is on the X. In the dual, feasibility is on these D, dual slacks, or reduced costs, whatever you want to call them. We have pricing step. We have an F-trans step. The position is reversed. We have a B-trans step. The positions are reversed. This B-tran looks different from this one because I wrote the alpha here. There was a reason for that. But the alpha appears down here at the bottom. So you're really doing the same thing. The F-tran and the B-tran are the same. And the ratio test is a ratio test in each case. But they're different ratio tests. If you just compare these algorithms as written there, the amount of work per iteration is virtually identical. The only difference is that the biggest difference is probably in the ratio test, where in the primal, you're computing some ratios and taking a minimum over the rows in the problem. And in this dual, you're taking ratios and a minimum over columns. Typically, linear programs have many more columns than they do rows. So that's typically a more expensive ratio test than this ratio test. As described here, that's the only real difference. But in practice, actually, there are other big differences that are all hidden in this description. If you know the primal simplex algorithm, here it is, in one description, you know in this pricing step, you don't have to do what I said here. I'm saying pick the most negative reduced cost. But in fact, the algorithm works perfectly okay if you pick some negative reduced cost. So you don't actually have to compute all of D in the primal algorithm. You can just start compute a value, compute another one. If you find a negative one, take it. And hence, you don't really need this entire vector to implement the primal simplex algorithm, depending on how you do it. All right? That freedom is masked a little bit here, but it exists. You don't really have that same freedom in the dual. You pretty much have to do those calculations. You can't avoid this calculation of dn because you need it to preserve feasibility in the dual. So at least a first pass implementation of the dual is actually considerably slower. There's considerably more work. Odd, because I'm going to claim that the dual is faster. Seems a little bit strange. Okay, so here's a summary. What we've done, we've defined the primal and dual linear programs, tried to get used to some of this notation so we can do the stuff that comes later. We proved the weak duality theorem, introduced the concept of a basis, and stated the primal and dual simplex algorithms. Left to do is to show correctness of the algorithm, enough so that we understand what the steps mean. For example, when I say it's optimal, is it optimal? When I say it's unbounded, do we know it's unbounded? Well, these are not hard things to do, but they're informative and describe, really this is the essence of it, describe some key implementation ideas. And that will bring me to the first slide of the next part, which is this. So for this part of the presentation, I have a natural disinclination to go firing through lots of formulas and not really explaining everything and so forth. I much prefer to explain things in detail if possible, but I think it won't be possible in this part. I will have to fly over some of the details. I'm, of course, happy to discuss afterwards and or point you at places where you can get more details. I think there's a sense there's a certain advantage to moving along at a reasonable pace so that you at least get a sense of the landscape of the kinds of things that are involved. On the other hand, maybe I'm completely wrong and you'll find it utterly straightforward. I'm just getting to be so darn old, everything seems hard. Anyway, that would be the preferred outcome. All right, so dual simplex algorithm. We're going to analyze it with sort of a mix. We can sometimes actually analyze the dual by looking at the primal because of this one-to-one correspondence. So in some cases it will be more convenient to talk explicitly about the primal, but the goal is to understand the dual simplex algorithm. So we want to, in some sense, come to the conclusion about the correctness of the algorithm. That's a useful exercise. That when we say the solution is optimal, that conclusion is correct, and we've actually already proved that. Right? That was that important fact that said when you take these basic solutions that are in one-to-one correspondence with each other, that the objective function values are always the same, and therefore from weak duality, it follows that as soon as it becomes feasible in both problems, it's optimal. So that optimal, or that conclusion in the pricing step about optimality, we have in fact proved. The unboundedness we have not proved, and we'll come back to that. We will talk about finding a starting dual feasible basis, or showing that no such feasible solution exists. One or two tricks there. Talk a little bit about the input conditions, that they're preserved, not so much. And we will come back to the finiteness eventually. Just a minute now, Eli. Okay, there's a slide here that has a summary on it. For some reason, I guess that's further along. Okay, so let's talk about dual unboundedness. I'm going to do a useful calculation. Here's a summary of where we are. This is the dual problem with the slacks added to it, those Ds. We imagine we've selected an entering variable, one of these DBIs, and we've selected a leaving variable that's leaving the basis relative to the dual representation. The idea is currently DBI is equal to 0, and we selected this BI because XBI was negative. It's a violation of primal feasibility, and that motivated us to increase this D to some positive value, leaving the other components of DB at 0. That's the way the simplex method always works. We take a single non-basic variable, leave all the others at their current values, change it, look at the effect on the basic variables and on the objective function. Okay, so letting D underscore and pi underscore be the corresponding dual solutions as a function of theta, we obtain the following formulas. So the first formula is quite simple. That just says that the ith component is going to be equal to theta. This is a unit vector. And all the other components of this stay 0. So that's what we set up at the top. And then if you simply plug this in to those dual constraints and work out the algebra, it's a pretty straightforward calculation, you get a formula for the new values of the pi variables in terms of the old values minus theta times this z vector. That's the solution to one of those linear systems that we solve. All right, so that's a known vector in the algorithm. And the update of the dn's is given by the old values minus theta, again, times something we compute, this alpha vector that was computed from the inner products with all the columns, all the non-basic columns. So those quantities are known to us. So go to the next slide. Again, I've repeated those formulas at the top. Using theta greater than 0 and the fact that this is a primal infeasibility at this variable xbi, we get the following calculation. The new objective is equal to, right, pi is all that appears in the objective, so it's pi times pi transpose b. These are the new values of the pi's. We substitute that formula in, multiply out, we get pi transpose b minus theta times an expression for z, so I just went back to the definition of z and plugged it in, times b, and now you can observe that pi transpose b, that's this thing repeated over here, theta times ei, ab inverse b, those are the values of the primal basic variables, right? And now ei transpose times xb just picks out the ith component. That's what that unit vector does, and so you get the old objective, which is this thing, minus theta times xbi, which is negative, and so it follows with theta positive that the new objective is bigger than the old objective for theta positive. And that's good because we're maximizing in the dual. Right? So that justifies taking this step. Now, if alpha n is less than or equal to 0, this was what we looked at in the ratio test in the dual to conclude possibly that the problem was unbounded. If every component was less than or equal to 0, we claimed that it was unbounded. Well, as you can see here from this formula, if theta is less than or equal to 0, then dn stays non-negative for all values of theta, making theta arbitrarily large, so it preserves dual feasibility and makes the new objective arbitrarily large, so the problem's unbounded. Right, so we proved unboundedness. On the other hand, if theta is not less than or equal to 0, meaning at least one coordinate is strictly positive over the index set n, right, then to preserve the non-negativity of this vector of the dual slacks, you easily conclude, this is the familiar ratio test computation, that every time a positive alpha occurs, theta can't be bigger than the ratio of the corresponding component of D and the corresponding component of alpha. Whoops. I don't know what I did. This is just, the reasoning is just exactly the same as the reasoning you're familiar with from the primal simplex algorithm, namely that you take the minimum of these, and that's the maximum step size that you can take. That gives you this ratio test. Okay? So, let's see what's on the, yeah, okay. So, the fact that feasibility is preserved in the algorithm, because we need to preserve dual feasibility, as we just argued, that follows from the way we do the ratio test. So that's been proved. We need to conclude that non-singularity of the basis is preserved. I do not propose to go through the details of that. I list here two update formulas for the basis, one for the basis and one for the inverse. And all this formula says is that you're taking one column out and putting a new column in. So were I to go through verifying that, it would take us literally 5 or 10 minutes to write it out. We don't have the time to do that. But these formulas are very useful, and non-singularity follows by simply multiplying these two and seeing that you get the identity. That proves that this first thing has an inverse and therefore that it's non-singular. All right? So there is a very short way to show that you preserve the non-singularity. Finiteness. Let's talk about finiteness. So if this is, again, a familiar argument that I'm going to make to start. If you took linear programming at some point, you surely saw this, have seen this argument. If at every iteration of the dual simplex method, every component of dB is strictly positive, where B is changing all the time, but if that vector, every component stays strictly positive, then the dual simplex method is finite. Why? The dual objective, the ratio test will always yield a positive value. Therefore, the objective in the dual will always increase by some positive amount at every iteration. But the basis uniquely determines the value of the objective, so no basis can be repeated. There are a finite number of bases, therefore the algorithm is finite. All right? Now, of course, this would correspond to a massive assumption about non-degeneracy, which doesn't hold in practice. Typically, real problems are massively degenerate. The majority of the variables are actually equal zero, frequently. So this condition doesn't hold. So what do you do to guarantee finiteness? Well, the standard thing that I think virtually everybody knows about is this beautiful combinatorial rule that Bob Bland discovered by studying so-called oriented matroids, and leads to a version of the simplex algorithm that is provably finite. Unfortunately, Bland's rule is an absolutely terrible idea from a computational point of view. It determines the incoming variable. It determines uniquely the outcoming variable. It doesn't pay any attention to the sizes of the reduced costs. It doesn't pay any attention to any numerical issues. It is truly a disaster. But it is a beautiful combinatorial rule and simple to state. If you read Vashek Fatal's book, I find it amusing. He states the rule and then he says, and the proof is easy. Vashek has a very different notion of easy than I do, that's for darn sure. The proof is short, but short is not to be confused with easy. It's tricky. What Gurobi does in practice, what Simplex does unless they changed it, and what I guess Express very likely does, is uses a perturbation to guarantee with very high probability that in fact dB is strictly positive.